Hello all, and welcome back to Getting Started with Python Machine Learning. We're starting a new section about modeling complex relationships with nonlinear models. We talked a lot about linear models both for classification and regression in this course. As a reminder, linear models is when the feature's effect on the target is linear, or you can describe it in a straight line if you plot the feature against the target. A nonlinear feature means that when you plot the feature against the target, the relationship between the data points on that graph is not a straight line. So it can be a line curving up rapidly, which is an exponential relationship. It could be a line that goes up but eventually tails off, a log relationship, or even be a wiggly line, which signals a more polynomial relationship, maybe quadratic, maybe cubic. In this section, this is what we're going to take a look at. How can we model relationships that are not linear, and what kind of machine learning models can we think about when we see this relationship between our features and our targets. I'm going to explain this in 4 simple videos. In the first video, we're going to talk about creating explainable models with decision trees. In the second video, I'm going to talk about automatic feature engineering with support vector machines. In the third video, I'm going to talk about dealing with nonlinear relationships with polynomial regression. And in the last video, I'm going to talk about reducing the number of learned rules, or reducing the magnitude of the coefficients that you have learned in regression with a technique called regularization. In this video, I'm going to focus on creating explainable models with decision trees. In this video, to create decision trees and explain them, I'm going to show you how, number 1, we can fit a simple decision tree to the iris dataset. And then number 2, using an inner property of our decision tree model to extract some rules. Number 3, constructing a recursive visitor to the decision tree. Obviously, a very important question is, what is a decision tree? A decision tree allows you to stack rules, like if sepal length is smaller than 3, then look at sepal width. Otherwise, look at sepal length and see whether it's larger than 5. So a decision tree basically has a rule in the middle, and it allows you to branch out in 2 directions depending on whether that rule is true or not. Because when we stack many rules, one on top of the other, where the terminal nodes, or the decisions where it's not a decision but it tells you a label, is one of the labels in the classification task, it allows us to capture nonlinear relationships between the features and the targets. So this is what a decision tree is. When we use a recursive visitor to explain the rules of the decision tree, it will be much more apparent what decision trees can do and how they look like. But I'm sure you've already thought about decision trees in your life, and this is how to do it in a machine learning way. We're back in our Jupyter notebooks, and we're looking at the notebook for section 6, Nonlinear Models. Let's look at decision trees. In decision trees, we first import the standard NumPy and train test splits. We import load iris, and all decision trees are placed within the submodule tree in scikit-learn. Easy enough. We load the iris data as usual. The way we start a decision tree classifier is very easy. We create a model and we instantiate a decision tree classifier. You can use the decision tree regressor for regression tasks. You can use more complicated trees like extra trees or boosted trees, and you can find these variations within the scikit-learn documentation. But today we're going to use a simple decision tree classifier. Like any other model for a classification task, we simply then fit it into the training data. To extract the rules from the decision tree, we can use what is called a visitor model. This is a concept borrowed from object-oriented programming, where we create a visitor and the visitor does different things depending on what the node it is visiting and the type of node that it is visiting, right? So if you put the visitor in the root node, then it would just say, okay, there's a root node, let me capture what row it is here, and then visit both the left branch and the right branch. If I hit a leaf, or a terminal node, or a node that isn't a row but is a decision, then I would simply stop myself, and this way recursively we can capture all the rows and all the terminal points in a decision tree structure. To do that, we need to import _tree from scikit-learn, and that allows us to see the types defined in the decision tree model. We create a function called findRows, which takes in the trees and the feature names. We take the tree's structure by taking the property from tree. The property is called tree underscore because we're inspecting the internals of a decision tree model. The variable namings within the scikit-learn library for these things are slightly more confusing. Anyway, we'll assign the internals of the tree, which is tree.tree underscore, into a variable called dt. We'll create a visitor function which takes a node and its current depth. The current depth is needed because we want to create a sensible indent whenever we go down a level. If this node isn't undefined, we first print the node's row, and this is simply the indent plus the feature's name plus the threshold. And we know that this row is always in a form of less than or equal to. We then send the visitor down the left branch of the tree, increasing the depth parameter inside the visitor function so that the next time it prints something, it will be indented nicely further down. After the left branch has been explored by the visitor here, then we'll send it onto the right branch in this line 11. Again, using the same logic where we increase the depth passed into the visitor function. If we have reached a node that doesn't contain a row, but contains a terminal labeling decision instead, we then just return the value of the node. We start the visitor at the roots of the tree, and so we apply findRows into the model, and feeding in iris data's features names, we can see exactly how a decision tree looks like. So you have rows, so for example, if cpol length is smaller than 0.8, then return the majority class being the first class. So you can see here, the decision is not labeled in terms of its strict label, but rather it tells you how many data points of this class is in this decision node, and how many points of this second class and third class is in here. So here what we interpret this as is, if the cpol length is smaller or equal to 0.8, then we'll just say that all the time, 100% of the time, we'll label this as class 1. Otherwise, we'll see whether the petal length is smaller than 4.75. If that's the case, then majority of the time we label it the second class, but then there's a small percentage of the time we can label it the third class. Whereas if petal length is larger than 4 3/4, then on the majority of the time we label it on the third class of the flower, and sometimes we label it on the second class. So it gives you sort of probability of how likely this is in a certain class if we have arrived at this node in the decision tree. And that's all there is to it. So we've just learned, number 1, what is a decision tree? Number 2, fitting a simple decision tree to the iris dataset. Number 3, using an inner property of our decision tree model, .tree underscore, to extract rows from the decision tree. And lastly, constructing a recursive visitor to the decision tree.